from University of Minnesota to give a seminar today. So he's a full professor at the University of Minnesota since 2004. He obtained his PhD from FU Berlin in 1994 under the supervision of Bernhold Fiedler. And after he got his habilitation from FU Berlin in 2001, he joined the School of Mathematics of University of Minnesota as an associate prof. And he won the Siam J.D. Crawford Prize in 2009, received a Humboldt Research Award from the Alexander von Humboldt Foundation in 2016. And at that same year, he was named a Siam Fellow. From 2013 to 2018, he was the editor-in-chief of the Siam Journal of Mathematical Analysis, and his research interests are concerned with patterns and waves in spatially extended dynamical systems. And he's been working on existence, stability, bifurcation results for coherent structures, such as wave trains, invasion fronts, pattern-forming fronts, defect in oscillatory media, spiral waves, or defect in striped faces, such as grain boundaries and dislocations. So without any further delay, then I would like to give you the floor, Arnd, and please, you may begin.
Yeah, thank you so much, Jean-Pierre, for the kind introduction, and more so for the opportunity to talk about the things that I find really interesting and challenging in the past and in the future. So I'll be very light on details and just sketch sort of some of the problems that I think are worth taking another look or taking a first look in the future. Many of them are, as I think people here are used to, sort of in combination with analysis. Some need progress in analysis, some might stimulate progress, and hopefully there's something in for you. Please feel free to ask questions, in particular, whenever after the talk, if you think, well, that was unclear or so, drop me a note. I'd be happy to give you more references or so. And during the talk, I have basically 3 sections, like 1 to 3 from left to right, here, front spirals, defects. And so maybe I'll take a short break after each section. If there is a quick question or so, we can probably interrupt and then come back to it in the end or so. So with all that said, I'll give you a quick outline here of what I want to talk about. First section, I'll talk about front dynamics, very old subject, which I believe is worth revisiting. We've been making some progress there from an analytical side, and I think there is a lot of interesting and important problems in terms of computational approaches. Second one is about defects, also an old topic. Defect dynamics, these are mostly wave sources that I'll talk about, but I'll point to some sort of outstanding problems that seem to be out of reach for analysis after people having tried for so long, but with a little help from computers, we might get somewhere. And the last one, I'll be a little bit vague and point to some things that we've been doing in terms of getting beyond the strict dynamical systems approach that dominates the first problems that I'm talking about. And so this is truly sort of outward and forward looking. Okay, so with all that said, let's get started. Here's a few pictures. So why front dynamics? And when I'm saying fronts here, I'm saying invasion fronts, right? So this is propagation into unstable state. Why is this interesting? Here's an example that's sort of analytically still to a large extent out of reach, but here's an equation with lots of interesting phenomena, I think. So this is the Cahn-Hilliard equation. Many of you know that equation very well. What you might not know so much about is what happens with invasion fronts. So the equation is a model in all sorts of circumstances because it's so simple. It's in conservation form, has all sorts of symmetry, so comes up in scaling limits, and it first for us just a model for phase separation as a conserved quantity. It's in divergence form and has lots of constant equilibria, right? If I set u equal to a constant, then the right-hand side is 0, so nothing changes. And you linearize, you see that constant states close enough to 0, it's known as the spinodal regime, are unstable. So if you start with such an unstable state, that is in these pictures happens to be the gray region. Why is this black? I don't want to get into this. So there's this gray region. These are unstable. And what I'm doing, I'm perturbing on the left edge. And then time goes up and you see this unstable state destabilizes. And what you see is lots of fine patterns. These are stationary in time, so vertical stripes. You see those everywhere. These are stationary in time patterns. And they emerge along this fixed slope line. The inverse slope, because this is time space, is the speed, right? So the steeper this line, the faster these patterns invade the constant state. So this is spinodal decomposition, it's called because U roughly attains the values plus and minus 1, which are energy minimizers, while starting from something close to 0, which is not an energy minimizer. All right. These patterns, on the other hand, are also unstable. And you see this in this secondary fronts, which come up here. So you're forming from these patterns here, you see every other of these stripes disappears, and you see a coarser pattern. So there's a second front with a different slope. It's a coarsening front. And if you make these pictures much, much bigger and run this for much longer, you will see a tertiary front where you see another period doubling. So you actually get a period doubling cascade in terms of wavelength. It's not always period doubling. Sometimes you see other wave numbers, but you see these cascades of fronts. And of course, dynamical systems, I don't have to motivate you finding this interesting, right? So this is one example. So there's lots of interesting phenomena. Describe these slopes. What are the slopes? What are the wave numbers that you see here? Why, if you look at this, here's a coarsening front, and here this coarsening, if you look closely, you see the little wiggles. They're a little hard to see, but this secondary front here has caught up with the first front, and you see something that you'd call instantaneous coarsening, right? So when does this catch up? Can we understand this? This is some kind of dynamics that are happening here, but how do we describe these? How do we understand those, right? So I wrote a paper about this some 5-10 years ago or so, which mostly is about existence of such fronts and some predictions, but very little analysis in terms of what are actually these fronts that you see here. Why is it hard? Well, if you run these simulations and you want to be sure, then you make the domain larger and you run time for longer. And then you see what's down here. And that looks very fuzzy. Right, and it looks fuzzy because of round-off errors. You find various articles that can explain somehow the width of this, right? But it's really purely determined in terms of round-off errors. And I do not know of a way how to get good data, how to run simulations that do not suffer this problem. The reason you see round-off errors so dramatically here is that everything you see in these pictures, every state in Cahn-Hilliard is unstable. All these patterns that you see are unstable. And in this large domain, they're actually unstable against the essential spectrum or lots and lots of eigenvalues, clusters of eigenvalues, very unstable. So that if you want to observe these states, they are formed exactly through the fronts in theory. Round-off errors mean you don't have them exactly, you miss out somehow. And so you might have an error of 10 to the minus 16, which of course, when you have exponential error growth, we all know this is not a very small number. So after a finite time here, 50, 100 or so, you see errors taking over. There isn't a good setup that I'm aware of that would run this experiment for arbitrarily long times. Okay. So the question here is, of course, this question of propagation into unstable state goes back to the 30s of the last century, right? So Fisher and Kolmogorov, Petrovsky, Piskunov, they studied this very simple equation, which is much more tractable because it's a second order equation, it has a comparison principle, and you can find these invasion fronts by basically doing phase plane analysis, right? These are sort of very popular exercises in undergraduate classes, finding these fronts. So this front here has, instead of this constant mass state in Cahn-Hilliard, it just has 0 that's unstable. And the state that is created here, u equals 1, is now stable, rather than, you remember these patterns I told you, they're all unstable. So here you just go from an unstable state to a stable state. So if you start with sort of step-like initial condition, you see over time, just like in the previous pictures that I showed you, a front developing. And this front propagates with speed 2. Why 2? Well, if you look for traveling waves in this equation, you look at traveling waves happen to be saddle sink heteroclinic orbits. There's a whole family of them. Actually, they exist for all speeds. They happen to be monotone only for speeds bigger or equal than 2. But being monotone doesn't strike us as a very good criterion, given that all fronts are non-monotone in the previous pictures that we saw. What's more important is that fronts with speed less than 2 are actually very strongly unstable. I'll mention this a little bit later. So anyway, there's fronts with speed bigger, equal, and less than 2. So what's the speed? That's one of the information pieces that we really wish to know. What's the speed? Well, this is back in the 30s. In the KPP paper, they saw how to establish that 2 is the right number out of all these. 2 is the right number, and it's a very simple comparison principle argument where you take one of the fronts that has speed just less than 2, you take it up to the first 0, and then you max 0. You just take 0. So what you're taking here locally for a solution is something that is a solution, and something that is a solution, and then you're taking a max of the 2, and that makes you have a sub-solution. So if you start above this, say with a step function, you stay above. So you have to propagate with speed at least 2 minus epsilon. You can refine this argument. There's a lot of beautiful analysis, lots of work going into showing that this speed is actually converging to 2 very slowly, with rate 1 over t, with a universal coefficient, and so on. Bramson and more recently PDE techniques have shown that there's a log shift in the position and so on, all relying on these comparison principles, right? But this is a way to see why, for steep initial data, you always see the speed 2 when you have a comparison principle. Right. Now, in the literature, in the more experimental or theoretical physics literature, you will see that this has nothing to do with comparison principle. And in fact, you can predict spreading speeds in all these other systems that I showed you and many, many others, and it works just fine. So there seems to be much more universal mechanisms at work that do not rely on comparison principles. But there is, to my knowledge, not a single argument that tells you about selection without a comparison principle in the literature. So here's an example just to describe the problem without being able to rely on comparison principle. Take a 4th order equation. These equations come up in all sorts of circumstances, depending on choices of parameters here, alpha, beta, and so on. A 4th order equation do not have comparison principles. What's the spreading speed? U equal to 0 is unstable given the right signs of these alpha and betas and so on, right magnitudes. So U equal to 0 is unstable. And so what's the invasion speed? You have another equilibrium that's U equal to 1 that's supposed to take over maybe. What's going to happen? Well, what you do is you forget about the nonlinear part, and then you can solve explicitly. And there's this machinery that goes back to the 50s, actually, in plasma physics. How do you determine if a state is pointwise stable? And what you have to do is not Fourier transform and compute fastest growing Fourier modes, but what you do is like extend Fourier transform in the complex plane. You get a complex dispersion relation here. This comes from Fourier Laplace. So you do lambda is the temporal exponent, and nu is the complex spatial exponent. So you just replace x by nu and you get this dispersion relation. And instead of looking for fastest growing modes, which you might do in another context, here you look for these double roots with a pinching condition. So I'm not going to explain to you. Matt Holzer and I wrote an article that sort of makes this a little more precise, sort of some of the knowledge that's in the literature, phrases it in more sort of terms that we're used to in dynamical systems in particular, and explains all these concepts of marginal stability and spreading speed, what this has to do with dispersion relations. Marginal stability then says this criterion, the pinch double roots, they tell you how fast perturbations grow pointwise. Marginal stability says you go in a frame that moves almost too fast. Too fast meaning if you move very fast, things will decay pointwise. If you don't move fast enough, things will decay pointwise, grow pointwise. And at criticality, you have one of those pinch double roots sitting on the imaginary axis. And that gives you not only a speed, that critical S, but also a frequency from the lambda. So that determines the invasion mode. The frequency gives you then this wave number together with the speed that you saw in these very first pictures, right? So these are linear calculations that's to some extent explicit, right? You have Fourier Laplace, right? Except for the fact that you have to deal with fourth order polynomials. But nonlinear, of course, this doesn't help. So what you would like here is to say something like this, to get a nonlinear selection in such a, say, fourth order system, which does not depend on the exact shape of the system. So it should, like in dynamical systems, you want to linearize and infer information about the system from these sort of coordinate independent linear information. It shouldn't depend on the exact shape if it's a second order or a fourth order operator. And the second thing we don't want things to depend on, we want the selection to not depend on the sign of the initial condition. So we want an open set of initial data that selects a certain invasion mechanism that selects this front. So what we've been doing, that is mostly a student of mine, a graduate student, current graduate student, Monty Avery, who has done all of this work and has pushed this program through so far, is trying to get such a nonlinear selection result without using the comparison principle. And I go very quickly over that, won't tell you how and what, but just tell you sort of these basic, what I would call conceptual assumptions. Rather than saying we need a specific equation, I tell you what does the equation have to do, right? So conceptual assumption, I want a front at a linear spreading speed. I can compute this linear spreading speed from linear information, connects a stable state in the wake, an unstable state in the leading edge. We are going to require that this selection is stationary, so I don't want oscillatory front propagation. I want this front to be marginally stable in an exponentially weighted space. That is a little touchy. There's lots of examples. I come back to this. It's true in most of the example that we're looking at here in these fourth order examples, but might not be true in general. And then there is an additional criterion which says, I want to avoid transitions to pushed front. So I want to avoid the nonlinearity being on the verge of taking over. This is sort of a non-degenerate assumption. It's generic. And so we need an absence of a resonance, a bounded eigenfunction. And the framework, to avoid some linear algebra, we believe this works for systems, but we're going to take just a higher order scalar equation, right? Where this P can be a higher order polynomial, right? And then Monty, together with Louis Renaud, showed that these assumptions are actually open assumptions. We made this a little more general in our current paper. Monty showed that these go from KPP, where they're valid, to a higher order equation. It's a singular perturbation problem. And the more interesting result here, that's what I believe is a first result of this type in this context, is that Monty proved here is, under these conceptual assumptions, the front and the speed are selected. What do I mean by selected? I mean that they attract, the front attracts up to shifts that are little o of t, meaning the derivative goes to 0. So the speed is actually selected. This is a shift of the front position that has 0 speed asymptotically. It's a log shift, can be more precise. It attracts an open set of steep initial conditions, including compactly supported data. So this is what I would call the selection problem. Show that compactly supported data, an open set in a suitable topology, is attracted, propagates for this speed. So with that result, that should be on the archive very soon, in a week or so, we can now talk about the selection problem and think about, when does this work, when does it not work, and study systematically invasion processes. There is, just to be clear, there's a few things that we do not cover, hopefully not yet. So there's certainly things that we are thinking very much about. That is, what is lambda star is non-zero. These are oscillatory. These are these pattern-forming fronts that you saw in the beginning, for instance. So when the leading edge has an oscillatory motion. Marginal stability in the wake when you have patterns, or even instability, as in the Kern-Hilliard example we can't deal with yet. And then there is a wealth of really interesting examples that Matt Holzer really started working out with examples and proving things, mostly relying on comparison principle, but clearly seeing that there is a whole world of interesting anomalous spreading phenomena where you have fronts that are clearly selected and can be stable, but they're not stable in any exponential weight. So this is something we cannot address, but really interesting problems for the future. So where do numerics come in? Other than doing these direct simulations, right? I mean, right in the sense you know when you're seeing a round of errors and when you don't. There's very few examples where you can actually prove the assumptions that we have here. And I believe this fourth order group of problems here that I'm writing up here again is a good class of problems where we can have sort of a prototypical class of problems. Or we can say, hey, in this class, we know spreading speeds. I have 3 parameters here, but you can scale, get rid of one of the parameters, right? Scale time, and then you just have 2 parameters. There is, from an analysis point of view, there's a couple of limits. One of them is the KPP limit when alpha is 0. That's something that Monty and Louis did in their paper. There is another example, when you choose these coefficients right, you get what's known as the Swift-Hohenberg equation. And that was sort of proven in the sense that, our theorem doesn't apply there. So, but that can be reduced in some limit to the Ginzburg-Landau equation with some elaborate analysis. You can see that it actually holds for this 4th order equation that goes back to Coley-Ekman and several works afterwards. There's probably other limits here that are of interest.
Aren't you writing alpha equal -1 there? You mean +1, I guess, or what is that?
Yeah.
Okay.
Too many minus. I wanted to make sure it's negative. I wanted to make really sure it's negative. So I made it negative twice. Sorry. Thank you. So these are, I believe, very tractable problems in a way, because what it amounts to is, at least in the cases where you have selection of like just traveling waves, these are just heteroclinic problems and spectral problems, many of which have been actually discussed in the context of this seminar here for combustion problems or shocks in Euler gas. So trying to establish the existence of these heteroclinic fronts and point spectrum, this is a very well delineated class of problems where one should be able to just say, hey, for this class of problems, we know what's true and what is not true. The conjecture is, of course, that in this case, you always find pushed fronts. Sometimes they're oscillatory, but stability in the wake and so on, there's probably actually phenomena going on here in these transitions from sort of stationary fronts to pattern forming fronts to oscillatory fronts that do not form patterns and so on, that I don't think are very clearly understood. There's also a problem that I don't think is very well studied, how to numerically check the absence of resonances, but that's I can talk about that at some point if there's interest. Here's another example that sort of leads into my the second part of this lecture here is, when do these assumptions actually hold? Here's another equation that is again prototypical. It's an amplitude equation that you can derive in many ways whenever you have small amplitude oscillations in a spatially extended system. It's the complex Ginzburg-Landau equation where you recognize, if you neglect this first term, you recognize something similar to the Hopf normal form, supercritical Hopf, where gamma is the nonlinear dispersion. And when it's spatially extended, the first term you would pick up is a diffusion term with a complex dispersion parameter alpha. So this equation again has Hopf bifurcation, an unstable state. And it has stable states, which are not quite equilibria. These are like oscillations that they're modulated in space. There's a whole family of them. Since this equation has this e to the I5 rotation symmetry, right, has this gauge symmetry, these are in a sense relative equilibria, sort of up to this rotation, they're just equilibria, right, which makes sort of computations and analysis a little prettier. You can compute what I showed you before. There's a linear selected speed, a frequency, and you can see what's selected in the wake. And you should be able to establish rigorously that these fronts exist for all values of the parameter alpha and gamma. Actually, when you look at fronts, you can get rid of one, the alpha and the gamma, through some little trick, change of coordinates. So it's really just a one parameter problem. Numerically, this seems to be true. And once you have those, you should be able to study stability. And again, it's not just sort of establishing rigorously something that everybody believes to be true, but there are likely instabilities and transitions that showing sharply where these happen would be very valuable for reasons that I showed you in the very first slide, because these instabilities are very hard to capture in direct simulations. So knowing where exactly those are gives you information about the actual quality of your direct simulations. Right. So this is as much as I wanted to say about front selection. If there is any urgent pressing question, I'm happy to elaborate here. Otherwise, I'll move on to my second part.
Can I ask something, please?
Yeah. Sorry?
No? Yeah. In the very beginning of the talk, when you showed the instability that you say is due to round-off errors, right?
Yeah.
So how do you actually establish that what we're seeing is due to round-off error?
You predict how long it would take for round-off errors to grow by looking at the instability until they're sort of order 1. 10 to the minus 16, you have an e to the lambda t times 16. You figure out what the lambda is, times e to the minus 10 to the minus 16. And then you get the width of this strip. Now you can say, well, you might just get lucky. Well, I do single precision calculations, and the strip goes exactly to half the length of the strip. That's why I'm convinced.
Okay,
Yeah.
thanks.
I have not gone through the trouble of going to quadruple precision and see the strips double in length, which would be the other side. But I'm pretty certain, right? You see this all the time.
Well, I also have a question concerning these fronts in traveling waves existence. So
Yes.
you could, in principle, you could plug in the form of the traveling wave or the front you are expecting into the equation, and then end up with a stationary problem, stationary ODE, which has the wave speed as a parameter.
Correct.
So that would be another way of proving existence, right? So
exactly, that's exactly what I mean. Yeah. Thank you for clarifying this. Yes. So it is, you know, the speed, and you're looking for a saddle sink heteroclinic orbit, where saddle sink gets a little touchy when you're in higher dimension, right? When you have a 6th order problem and so on. But it's usually, it's a robust heteroclinic, but you're fixing the speed and you're trying to compute a heteroclinic orbit. When
yes, that's right.
The invasion mode is stationary, when this lambda star, the critical, is real. If it's complex, like in Swift-Hohenberg or so, then you have a time periodic orbit. You're looking at a problem in a strip where after Fourier decompositions and so on, you get an infinite dimensional traveling wave problem. So many of you have seen this. It is, I believe, still doable. And you, I believe, have done similar problems in strips. So this should be within reach, I claim, not in my reach, but maybe in others. Yeah.
Okay, thank you.
Yeah. Yeah, thanks for clarifying. Yeah. So maybe I'll move on here. And yeah, and please sort of, if you have other questions afterwards, that things that were unclear here, because there's a ton of stuff here, drop me a note or so, I'd be happy to clarify. So again, the big Ginzburg-Landau equation, right? Which was in '84, there were some curious solutions found by Nozaki and Becky. And if you want to read sort of an overview, there is an article aptly titled The World of the Ginzburg-Landau Equation by Aronson and Kramer in 2001, which has, I don't know, more than 100 pages, more like 200. And it will sort of give a good overview of the literature until then, which is fairly good because sort of people pushed this as far as you can using asymptotic and simulation, sort of as asymptotic simulations and explicit solution methods. So what they found is an explicit family of solution, and it looks like this. These are time periodic, so you use the gauge symmetry, you find time periodic solutions, then you stick in a traveling wave ansatz. That's a second order ODE, so it's a 4-dimensional ODE. Okay, you have this gauge symmetry, so it's really 3-dimensional. And you're finding heteroclinic orbits. These look like sort of the amplitude looks like a hyperbolic tangent. That's not true. It's much more complicated, right? These are big formulas. Nobody wants to read them right now. You can look them up in the papers. And the phase, if you look at this, goes like the tangent is roughly 1. So it goes like C, or when the tangent is -1, it goes like minus C at plus and minus infinity. So these are actually solutions where you see waves going to the right and to the left from a point source. And actually they're antisymmetric, so they have like a charge in this simple sense, right? So they're because of the tangent, but that's not all that important right now here. C is a parameter here. So these are, why are these important? Because they're pacemakers. So they send out waves. So, well, let's back up for a second. So this is a system that describes oscillation, spatially extended. And there is a huge literature, even popular literature, about synchronization. How do spatially extended systems synchronize exchange information? Usually this is a very slow process, a diffusive process. But in this example, it is much faster. You get frequency synchronization through these wave sources that send out information and wave trains. So that's this information travels out at speed order 1, and thereby sort of frequency synchronizes large swaths of your extended systems. So these are interesting. They're sort of really curious in this Ginzburg-Landau equation. If you go to 3D up to this gauge symmetry, you compute these, the Morse indices, so unstable dimension of these orbits, you get one-dimensional unstable and stable manifold. You're in R3, so you have a codimension 2 problem, right? 2 one-dimensional manifolds in R3. So you do a section, you're in R2, you have 2 points that you're matching in R2, and that's codimension 2. So you expect to see these for discrete values, omega and c, but you actually have them for a full family. So this equation is a little degenerate, and there's a lot of literature about resolving this degeneracy, but that's not what I'm interested in right now. For we have this family, it is explicit. C is a free parameter, and we want to understand when they're stable. That sounds again a little bit like a boring problem, right? Sort of, oh, we know they're there, now just prove stability. It is not. There is lots of phenomena associated with the fact that these are often unstable. So by the way, this degeneracy is often thought of as sort of a remainder of a limit where when you make gamma and alpha infinity, then you're seeing the nonlinear Schrödinger equation. And that is an integrable system. So this has a lot of special structure. And if you think of integrability being some sort of a miracle in the world of nonlinear PDE, then you can see where a little bit of this miracle survives for these dissipative contexts. So that's one way of organizing this knowledge. It's not really an explanation, just so to give you a little context. So there's lots of instabilities. There's instabilities in the far field. There is core instabilities where the core of this wave source destabilizes, starts to oscillate, becomes chaotic. Lots of others that I'm listing here. Why is this interesting? Well, it's one of the simplest models where we can study transition to spatiotemporal chaos, to turbulence. And it's been studied numerically and analytically in many ways. Here is a way to try to think of where does this transition happen and how does it happen in a spatially extended system. And these Nozaki-Becky holds play an important role in describing defect-mediated chaos, where defects play an important role in structuring chaos. Why is it relevant? Because we really don't know. Because we really don't know. There's literature proving stability and instability and showing boundaries, and people do not agree. Right? Every now and then, like in these days in particular, it's nice to have people agree. And so I think making this rigorous, you do a great service to the community in that sense. Analysis and simulation, sometimes there's gaps that have been pointed out in the analysis, and simulations, as I pointed out in the very beginning, are sometimes not so reliable when you're talking about instability and error growth, in particular in these spatially extended systems where you have transport. And it's not easy, right? But you have the solution explicitly. You're just talking about eigenvalue problems. And of course, there's many simplifications you can think of making, but the real problem has 4 parameters, right? Alpha and beta are parameters. C is that speed. And then you have the eigenvalue parameter. Right? It's not easy. It's a complex system even to describe your results. But on the other hand, that's why we started computer-assisted proofs in the first place, isn't it? Sort of to be able to do these seemingly unsurmountable tasks, right? The other reasons Nozaki-Becky holds are interesting is because they're the baby version of spiral waves. The defects in 1 dimension, 2 dimensions, these are very important structures that organize dynamics in many biological, chemical systems observed all over. They're fascinating because you watch a turning spiral, it fascinates you, it hypnotizes you, depending on the direction of rotation. They're also fascinating to me because I worked on them for so long, for some 10 years in the past. Here's an example where I believe one can really make progress using computers to solve these problems that were left along the way. And to go from there, right? Go further. So in 2 dimensions, same equation, the Ginzburg-Landau equation here, just with a Laplacian in 2 dimension. You can now look for waves that are point sources and rotating in space. So I'm thinking of this L here, those polar coordinates, radius and angle. Because of this gauge symmetry, you can stick this in. You get, instead of the dt, you get an I omega A. And you get the Laplacian in polar coordinates because of the L, the phi dependence disappears and just gives you this L squared over R squared. And what you end up with is an ODE with 2 parameters, 3, alpha, omega, and gamma. The L really is sort of a winding number, right? In phi, it's sort of a topological index. So call it the charge of the defect. It's, when you look at these, it's the L is the number of the spiral arms. How many arms does a spiral have? And so you get, this is again an ODE boundary value problem, right? As Michael pointed out, like most of these things that I've talked about so far are ODE boundary value problems in some sense. And you can simplify this, just divide by 1 plus I alpha, no rocket science here, relabel all these parameters. You only have 1 parameter, and you're looking at heteroclinic orbits now in the radial direction. You have to, there's a little subtlety. You want these spirals to send out waves. There happen to be in this equation 2 equilibria asymptotically. You stick something like this in, you stick in K, depending on omega, there's 2 values of K for each fixed omega. So you need the one that it has outgoing group velocity, which is a condition, something like this. So it's just an ODE, you're looking for a heteroclinic orbit. It turns out when you do the dimension counting, it turns out that the number of solutions that are bounded at 0, this is of course a 4-dimensional ODE, second order, A is complex. two-dimensional unstable, two-dimensional stable manifold at infinity, but you have this gauge invariance. You don't have translation because it's non-autonomous in R, right? So again, you have a codimension 1 intersection. So you expect to need this parameter omega, the frequency, to be selected, just like front speeds in bistable systems or so on. You expect this rotation frequency to be selected, right? By the way, this Morse index counting here is linked to the group velocity condition that I mentioned earlier, right? Why is this an interesting problem? Well, because it's this basic universal problem. There is very little in terms of analysis. If you set this gamma hat to 0, then you can set omega hat to 0, and all of a sudden you're left with a real equation. Well, it's not real, but you can make it real. You can consider the real subspace. And that has, again, monotonicity properties. You can do shooting, and existence is known and all sorts of non-degeneracies. Perturbation analysis like matched asymptotic by Pat Hagen in the 80s, Howard and Coppell did singular perturbation analysis to establish existence for gamma hat small. People believe it's true for all gamma hats. There is something in the literature that I cannot follow, saying there's a scaling argument that gets this to arbitrarily gammas. I cannot follow that reasoning. Numerically, they exist for all gammas, for L equals to 1. So one-armed spirals. They also exist for L positive 1, appear to be unstable. They don't seem to exist for L equal to 0. There's nothing rigorous beyond gamma small. But again, it's just an ODE problem, right? Boundary value problem, heteroclinics. Stability is even more interesting. Nothing is known. I think that's fair to say. I'm going to mention, so what do you have to do in the Ginzburg-Landau context? You plug in your spiral, you put a perturbation. Again, I wanted to make sure that the L is in there, so I put it in twice, and that's a little exaggerated because I factored it here. You don't need it here. So you modulate your spiral with a perturbation that could have a different azimuthal charge, right? This M could be different. So you could, for instance, perturb a two-armed spiral towards a one-armed spiral by choosing a different M here. And that's actually an instability mechanism. So you do this ansatz, you get a linearized problem, and you study stability, and you're going to find lots of interesting phenomena, right? Nothing is known rigorously with the exception of Pat Hagen's work using, it's not complete even relying on matched asymptotics. It doesn't treat the different M's here, just a couple of M's, some heuristics, M large shouldn't matter, small M seem to be okay. So there's evidence that this is doable. Some of it may be analytically in some limits, but in general, even for alpha close to gamma means you're very close to this real limit. Stability is not known. When I'm saying stability, I'm talking about spectral stability, which is the starting point to talk about any kind of linear or nonlinear stability. It's relevant because it is the modulation equation. It does approximate general systems near onset of half bifurcation. I proved a result in '98 showing that you can carry this approximation property over to show that these Ginzburg-Landau spirals actually exist in reaction diffusion systems close to a Hopf instability. Again, this is a little harder, right, than Nosaki-Becky. You have more parameters, alpha, beta, ln, lambda. You have to track these eigenvalues, but I'm hoping that doing some good numerics here, there's not even sort of non-rigorous numerics, right, in a meaningful way here. Of course, the real problem is doing this for excitable media where these are more interesting when the system itself does not oscillate, but has these large excursion as in Fitz-Nagumo here, which is this equation. I added a little diffusion to make it a little more regular. You don't have to. You would now look for rotating waves again. It's the very same problem that I showed before, except that it doesn't decouple in these e to the IL phi. So all the IL phi's couple together, and you have to look for solutions of, instead of just a heteroclinic in 4 dimensions, a heteroclinic in infinite dimensions. because of these 1 over R terms, the analysis is not so easy. And we finally completed a manuscript that lays this out. We as Björn and I, Björn Sandstede and I, that's going to be an AMS memoir. It's on our homepages that shows you sort of how to phrase this. This is even worse than anything I talked about until now. These spiral waves in reaction Fitzsinger-Gruen reaction diffusion system excitable media are amazingly robust. They're very easy to generate. They're abundant in experiments from chemistry to biology. There's no existent proof, not even formally without an honest gap, right? It's not like someone just has to do the analysis and make it rigorous. There are gaps. There is no existence proof. So anything you do there in terms of rigor is new, right? One thing I want to mention also, like when you do stability, there's all these phenomena here, breakup, meandering, far-field breakup, core breakup. Are they due to essential and point spectrum? Again, these are the questions that make us understand better transition to turbulence in spatially extended systems. One thing I wanted to mention leading up to my last section here, I have a couple of minutes, right? 5 minutes or so, is that in these equations, you always have these 1 over R terms. Let me just go back here, that are 1 over R squared. So these are a little cumbersome because you have slow convergence. So these make these boundary value problems a little harder. In the case of spiral waves, you can improve this convergence to high orders, R to the minus K, fairly easily. And that's worked out and shown in which topologies and function spaces you should do this in this article. Right. Basically, you're approximating, or you're constructing an approximate center manifold at R equals infinity that extends into finite R. Lastly, I have to cut this a little bit short here. I want to talk about what's beyond there and just talk about defects in striped phases now. This is a little more open-ended, and I try to show you a little bit what kind of things go in there, and I'm leaving this territory of heteroclinic orbits altogether, I believe. So this is the Swift-Hohenberg equation again. Now on the real line, something we studied as a first step towards doing what I'm going to describe at the bottom. And we added an inhomogeneity. So this equation has perfect periodic orbits, a whole family. So when you set epsilon equal to 0, or you go to infinity, this perturbation here vanishes at infinity. Then I have periodic solution with period something like 2 pi. So K is close to 1. But there's a whole family of those. So the way you can think about this equation, it's a 4-dimensional ODE. So you think about 4-dimensional spaces at x equals plus and minus infinity, and then the extended real line. So you make this autonomous by adding time as a variable, right? And now you have at infinity 4-dimensional spaces, left and right. And in these, you have like an annulus of periodic orbits, which is normally hyperbolic. So you have 3-dimensional shooting manifolds. And you try to match those at the origin. So you get 2-dimensional intersection, 3 plus 3 is 6, but you have a 4-dimensional system, so you have 2 left. So what we prove is you actually get a relation between these asymptotic phases of the periodic orbits and the wave numbers. And you can compute these. And so this is one way to look at defects, their relations between phases and wave numbers. Doing the same thing in higher dimensions is harder because you don't have that heteroclinic picture anymore. All of a sudden, you could have different orientations of your stripes left and right. We still prove some kind of perturbation result that's in preparation. I don't want to completely promise this. We have the linear analysis ready and in a form that we can do the nonlinear analysis. That's joint work with Scheel, Wu at Ohio University. So why is this hard or interesting? Let me give you a little bit. So we started doing this in work with Gabriela Jaramillo, looking at the Ginzburg-Landau equation with an impurity. When you do this, you can sort of wave hands. We don't do this, but just to for us to understand this now, you can go to polar coordinates, look at stationary solutions, and do some kind of center manifold, not quite, say, well, the radius is somehow, just look at these kind of nice plane waves. You can just stick this in. The radius is roughly the square root of 1 minus the length of the wave vector squared when you stick this in. And then you eliminate R by saying, well, the gradient is slowly varying. Do all sorts of approximations, which one can make rigorous in some sense, and you get a phase diffusion equation. If you stick in an homogeneity, this is sort of what you find. Now, when you think about looking for stationary solutions, and let's simplify things further, set phi equal to 0, say, a constant. So do this near phi equal to 0, then in some sense you're seeing Laplace phi plus epsilon g of x equal to 0. So you're solving the Poisson equation. And when you expand solutions, then all of a sudden you know what happens. You know, because since G is locally, like it's compactly supported, say, it's very localized. When you're looking far away at infinity, what is the stable manifold? You can say what the asymptotics are. They're the derivatives of the Green's function. You can expand this by looking at moments of G and then expanding the solution in terms of the derivatives of the Green's function, its partial derivatives. This is what's known as the multipole expansion, of course, from electromagnetics or wherever you want to look this up. And it's completely trivial, of course, for the Poisson equation. Doing this for Ginzburg-Landau or even Swift-Hohenberg is less than trivial. In particular, you have more than just the Laplace equation, you have Fourier-Bloch modes and so on. So this is what Gabriela did in this system and what we're trying to do with Scheel, trying to construct stable manifolds at infinity without actually talking about stable manifolds in these systems where you don't really have dynamics. It's always hard because you have this weak algebraic decay, not exponential as we tend to like it in dynamical systems. The last thing I want to say, I'm really running out of time here, is I want to give you an example for two reasons. First, because it's the last thing I've been working on, so I'm totally excited about it. And second, because it's an example of where you learn something about these defects. The previous one, they were, what I just showed you, were technical studies. What's going on with defects in these systems? How can you understand those? What's a stable manifold? What I'm telling you now is you can actually learn something about these self-organized defects. So what I did is here very briefly, too briefly probably for you to fully follow this, is we're saying replace in 2 dimensions in this phase diffusion equation, replace the inhomogeneity by a boundary at x equal to 0. Add a drift term if you wish so. So you're actually modeling growth of a striped phase, right? But if you don't want to, you can also leave this away. Add a boundary condition which mimics a little bit what I showed you before, this cosine phi. So I want the gradient to be roughly 1. That's the phase gradient in Swift-Hohenberg, say. And you can motivate this. You can actually derive this. PhD student of mine did this rigorously in simple problems. And at infinity, I want to have a constant slope. Right? So I do this in the half space. Now, if you compute solutions to this equation, you find traveling waves, you find stationary solutions, and you can compute the strain, the slope, this kx vertically, as a function of a lateral periodicity and the speed c. And you get what I would say are interesting surfaces. You can also say pretty, but they're actually interesting. You see this very caspoidal shape, you see a singularity here, interesting curves, right? What is going on to here? And I say this whole curve, this surface here, is organized by a transition from a defect to a different type of defect. And you can see this in this picture, where here, this is the same equation that I'll show you in a second. Here's the boundary. This is x. And you see where here, you see this gradual morphing of the stripes into the boundary at a weak angle. And here you see a very distinguished, like a curving. So this is what I would call a nonlinear self-localized defect. And this is just sort of a topological defect. And what do I mean by this? Well, you can actually say something about this equation. It's nice because this is a constant coefficient equation. You can use Fourier Laplace to play this into a boundary equation, which roughly looks like this, where the D is a pseudo-differential operator. So you have just a pseudo-differential operator on the boundary, and you can now talk about this differential equation where this is a non-local operator, but still you can think about heteroclinic orbits. And what you see when you're computing heteroclinic orbits, you have a parameter k and a speed as a function of the parameter, which is basically what I'm plotting here. There's a few twists. You see a transition. You always see this kind of kink in these curves. And you can understand this kink by closing your eyes, forgetting about the square root and saying, well, that's a similar problem. It's again, it's like a Hamiltonian to dissipative perturbation. And that problem you can completely analyze, and you see a transition from a saddle-saddle heteroclinic to, when you increase the speed, when c is very large, you see here, you have to choose kx equal to 1, you see a saddle node on a limit cycle. So this transition of heteroclinic orbits here is present here, but it's very different. Here, the localization, because of this square root, is always algebraic. It's actually 1 over root x. These numerics are really hard, take a long time. This is an ugly pseudo-differential operator. Lots of interesting things. I just wanted to show there are interesting things to find, learning about what is a defect. These are things that we've computed. We have no idea how to make some of these things rigorous. I'm out of time. Just leave up the summary. Thank you very much. I'm happy to take questions.
Many, many thanks, Arnd, for wonderful talk. Lots of open directions. So that was exactly the purpose of this. I'm very happy. Are there any questions or comments?
I have a comment. My name is Matthew Gudorf. I work with Predrag Svetanovich, or at least I did. I just graduated at Georgia Tech. So I'm really curious, or wondering if you have free time to talk more about these defects, because I work with the Kuromoto-Shibashinsky equation, which fits into your class of fourth order equations. And I believe I found such a defect. And in fact, there's a lot of details, but essentially, I have some continuous family of solutions which manifests as a relative periodic orbit, unstable, and the continuous family is essentially parametrized by differing phase shifts. So essentially, you can use these. I don't want to take over and talk about my thesis too much, right? I could talk about it all day, but I'm still in that mindset of thesis defense. But yeah, so I'm curious. I suppose if you took your equation and you thought of the spatial domain size as being a parameter, would you expect a family of heteroclinic connections to exist?
In time, you're talking about heteroclinics in time. I've been talking about heteroclinics in space, periodic in time. Now, okay. These often go hand in hand. I mean, right. In certain limits, I totally understand, sort of, but so in particular, in the Hamiltonian limits, this is a common thing. But so I don't know. This is probably something that takes more than a short question here for you. You actually do have to lay this out to me, and I'd be happy to listen to it, but maybe sure. This is not, I mean, you'd have to write something, and that's not the right context here. But I certainly, I mean, I'm well aware that such things come up not just in the Ginzburg-Landau equation. What I was trying to do is sort of show a few prototypical examples, and I give you any time that the Kuromoto-Shibashinsky equation is on the same level, if not even higher, of examples that one should probably study. But I was just trying to focus this in one direction, which made for this story. And I'd be very happy to learn more about, but maybe I need to listen for a longer time to what
Sure.
you accomplished there.
Sure.
All right. Other questions or comments? Well, actually, I have one. So, oh, Michael, I will ask first. Sorry.
I just pressed the wrong button. That's why I was a bit late. But please go ahead first.
Yeah. So, could you go back to your spiral waves slide, please, Arnd?
I'm working on it. Which one?
The one, yeah, let's say the one with the picture, and you had some ansatz.
This one?
Yes, this one. Yes.
Yeah.
Yes, this one. So, I guess in this case, it is not clear which ansatz to plug in order to get an ODE for that, right? I mean, if
it's
I look
not
at
an ODE. If you stick this in, the time derivative disappears. It becomes a phi derivative.
Yes.
Right. So you have an equation in polar coordinates which involves r and phi. Phi is on periodic boundary conditions. So what you can think of, like just for us now, you do a Fourier series in phi.
Right.
And then you say, I got 10 Fourier modes, I'm done. Right. Now you have 10 second order equations that all couple.
I see. And okay, I see. So in phi.
So of course you can extrapolate, you know what's going on, right?
Right, but say, so theoretically there would be infinitely many Fourier coefficients in phi. And in R, it would be all the way from 0 to infinity.
Correct.
Okay.
Right. So this problem is a little nasty because when you think about what you want is the regularity, right? What's the principal part? The principal part is you have a d phi here, second derivative, and that disappears at infinity. So when you want to compactify, sort of you look at what happens at r equals infinity, you lose your highest derivative, which is why we wrote an AMS memoir and not a short paper.
It is nasty. Okay.
Right. But it's once you see what's going on, it's not terrible, right? You have regularity. You can compactify. You just have to use the right norms and then everything works out. It's not terrible. Informal computations are correct because you still have this phi derivative. You have one phi derivative, and that's enough to make everything sort of pseudo-elliptic.
Okay. Okay. Yes. Thank you very much. But this is challenging. Yes.
Yeah.
Okay. Thank you. Thank you. I guess Michael, you had a question.
Can I add a comment on what you said about L? L over R seems to me to be the good Fourier coefficient because L, it's L theta. And if you want to have something which has the same value as a frequency, you should deal with L over R or theta. What do you think of that? Could that be useful?
I'm not sure. I honestly, I'm not sure I understood.
It means that when you deal with Fourier transform or with the Fourier coefficient, the L which is here is not the wave number because it has not the dimension of a wave number. I don't know if that can help you to understand what you can do when compactifying.
Well, okay, so in this example, in the Ginzburg-Landau equations, all these Fourier modes that I threatened Jean-Pierre with just a second ago, they all decouple. It's just the Ginzburg-Landau miracle, right? So you just have an ODE for each L. You can pick your L. And actually for each L, not 0, you find one of those solutions. These M-armed spirals, charge M exist. It's just, now when you go to this equation, there is no L. Instead of the L squared over R squared, you have a 1 over R squared d phi phi. And that is, of course, the dimension is what it is, right? And I mean, I'm not sure, maybe you were hinting at the sort of the kind of thing that we do when we say, when we want to compactify, you have to use a norm, of course, that is, as you pointed out, you have to have the right dimension. What you can expect is not a regularity necessarily of d phi phi, but of 1 over r squared d phi phi, or the associated spaces then depend on 1 over r d phi, which is the natural derivative dx dy, right? D phi is a derivative along this large arc, and you don't necessarily can expect this to be smooth, except that because of the dt, you have a d phi, and that does give you smoothness in the azimuthal direction, not just in x and y, in this kind of not length scale direction because of the rotation. It's a very funny thing, spiral waves. The speed of propagation at the spiral wave, when this guy rotates, then this pointwise, the apparent phase velocity of a rotation is infinite at infinity. It's arbitrarily large. Of course, group velocities are not, right? But just the phase velocity being so large leads to smoothness.
Yes, that's what I hoped, and thank you for the answer.
Yeah, it's probably not.
All right, so I guess Michael, now you are next.
All right, thank you. So in the meantime, I have actually 2 questions. So the first one just was generated by Jean-Philippe's question. So this is maybe a bit naive, but why is the necessity to go in with the equation which you just have on the screen to go into polar coordinates? Why can't we treat that directly as a PDE? And so to say, if we're thinking of computer-assisted terms, well, look for compact support approximations to find solutions of that problem.
Yeah, so sort of. I mean, yes and no, right? I mean, you can have lots of arguments about like this, view this as a heteroclinic orbit. Well, what you have to sort of accept though is that what you want, the limit, the spiral waves are very much defined through the limit as r, the radius, the distance from the center, tends to infinity. They're not compactly supported, so they're not like a localized structure. There are localized versions of spiral waves. That's a totally different story, and they're also interesting, but and maybe they're reasonable to start thinking about these problems. But the most interesting ones are these Archimedean spirals, right? Asymptotically Archimedean, and they are defined like, if you, for now, grant me this picture of heteroclinic, then there are heteroclinics in this non-autonomous, because of the 1 over r term, dynamics between the origin, 0, and a periodic orbit, a relative periodic orbit at infinity. Now, if you phrase the PDE terms,
So what I meant is I was not quite precise, of course, but as far as I understand, you know some asymptotics r tends to infinity. Right. You know some asymptotic form, and if you subtract that from the unknown solution, then you get a solution which decays at infinity.
Yeah.
And that was my idea. If you could approximate this by compact support approximate solutions, right? Not by it still doesn't have compact support, but you could approximate by compact support approximate solution, and then try some rigorous numerics.
I mean, in the end,
it's very vague, I know.
I mean, no, it's perfectly fair and fine, right? I mean, in the end, you have to decide, how do you want to discretize your system? Because these guys rotate, and because they have, that's what I just talked about, they have regularity d sub phi. So they have more regularity than you might think, right? For a solution to an elliptic equation, right? They don't have just H1 regularity, but these one derivative in the angle that actually goes like 1 over r, right? In this direction, right? If you think of orthogonal system, right? This derivative in x and y just in this direction, right? This is small. So that suggests that, now arguing as a numerical analyst, which I am not, you should spread out your grid in the azimuthal direction in a way where you only need a fixed number of points along every circle. So if you go in somewhat blindly and say, well, there's a big domain, take a big domain and do exactly you're right on the right track with your sort of stuck 6 something in that infinity and so on. But then you might be over discretizing in the azimuthal direction when you're going far out in the radius. So this scaling in phi is a natural thing. Now, should you use Fourier modes? God, I will not argue about this right now. This is maybe not the right thing. If you're looking at Fitz-Nagumo with a small epsilon, these are very sharp interfaces. Maybe Fourier isn't the right thing. Maybe different types of ansatz, adding a few extra modes that are not Fourier-like is the right thing. There is lots of knowledge that can help here, right? But the sort of, there is something that is, polar coordinates are not a bad thing, because there's the R limit and there is the phi regularity that are just in the problem. Yeah.
Okay, so what I'm suggesting might be doable, but it might be shooting at a small bird with a cannon, right? So.
Well, you want to be efficient when you, the way you discretize, in particular when you want to make it rigorous in the end, right? It's.
Right.
But I'm just, I don't know how it's going to play out really, right? I haven't even tried anything like this. There are good algorithms for computing these spirals in disks. Dwight Barkley has them on his homepage, and you can take those. They work really well, but they just put some artificial boundary condition. And that works really well for reasons that we also explain in this paper. You have very good convergence. But I don't know how well it would work making this then rigorous. So we have, so basically what we did is take a heteroclinic, truncate it. This kind of, if that's the sequence, suppose you have a solution in infinite domain, is it approximated by finite size problems, right? But we don't go like basically the Newton method, like if you have a solution. We haven't done the sort of, suppose you have a solution in a finite domain, can you conclude something in the infinite domain? That's not in this paper. But usually you should be able to do this, except that it wasn't exactly easy, right? There's these 1 over R terms, and these norms are, yeah, sorry, it's just what it is.
Oh, okay. Thank you.
So Michael, you said you had 2 questions. Did you ask the second one?
Remember that. So if I may, yeah. So yes. The second question is a completely different one. So that's connected with the spectral stability. So you have these. So what in principle you have to do, you have to prove that in order to prove spectral stability, that there is no eigenvalue lambda in the right half plane or in the left. I'm not sure how you normalized. And that's true for all these parameters. That's right? That's what in principle you have to do, right?
Yeah.
So that means again in principle. So there are methods for excluding eigenvalues from small circles, and so in principle you could cover any compact domain in the respective half plane by such small circles and exclude in each of these small circles you exclude eigenvalues. Mm-hmm. And then in principle you can do it by computer assisted means if you know a compact subdomain of the half plane where you know a priori all eigenvalues, all potential eigenvalues must be in that compact set. And if you have that compact set, then in principle, if you don't look at computer power necessities, then you could do it by computer assisted means, right?
Yes, yes. So I think these a priori estimates you could get, there is something you might like to hear since you're from Karlsruhe and so on. I'm sure you are very familiar with these issues. There's a very curious things coming about these eigenvalue problems because of the d phi, that spectral stability does not imply linear stability here. Yes. And because it's a strongly continuous semigroup with a d phi. So you do not have spectral mapping in a violent way where you can have exponential instabilities in norm, although you have spectral stability. This is a very sort of out of real life example for these kind of obscure functional and analytic results, which I thought was remarkable when we noticed it.
So I wanted to stick to spectral stability with my question.
Absolutely, do this. Then, yes.
Then you're saying we can get this a priori set where all potentials eigenvalues must be in, and then we could do in principle with a lot of computer power. We could in principle prove it, right?
Right.
Spectral stability
again. this is a little bit, yeah. I don't want to promise you too much here. I want to be careful because of, so bounding the real part is probably not very hard.
Mhm.
Bounding the imaginary part is not possible. So what you can probably do is you can bound the imaginary part of eigenvalues.
Yeah, that's what I mean. Yeah.
Right, sort of, I mean, sort of, you cannot bound sort of like, you don't get better and better estimates. It's not sectorial. You actually, the spectrum is, the essential spectrum is periodic with periods omega, I omega. So it's vertically periodic. So you have essential spectrum at 0 I omega, 2 I omega, 3 I omega, 5 million I omega.
Yeah, that
right?
makes it problematic.
So there is an actual problem, but I'm pretty sure we did not do this. It's interesting, actually, an interesting piece of analysis, probably, which I believe is one could do this. It should be true in a good world that you can exclude eigenvalues for very large imaginary parts there. You can push the essential spectrum in the left half plane with an exponential weight. So it's not that bad, right? So my guess is what you want, you can get it. You can't just pull it out of the literature, but it should be possible. Yeah.
Right, yeah,
Kind of
thank
what
you.
I'm trying to say.
Okay, are there questions or comments? Well, it's been already 20 minutes of questions, so I don't think we have to be shy to stop here. So thanks a lot, Arnd, for a wonderful talk and lots of new directions and ideas and motivations. So yeah, so as I said before, this Thursday we have the graduate spotlight on research. And next week we'll have a colloquium to end this first semester of the CRM camp seminars. We'll have a colloquium by Jean-Pierre Ekman. So hopefully we'll see many of you there. And once again, Arnd, thank you very much.
Yeah, thanks to everyone for great questions and for listening. And I think this will be posted at some point, right? The slides.
Absolutely,
so,
yeah, in a couple of weeks probably.
Okay.
Yes. So we can all go back and then try to understand really the nitty-gritty details of the open problems.
Yeah.
Okay, thank you very much, everyone. Bye-bye.
Bye-bye.
Thank you.